partial derivatives of a function in two variables. Let's begin by example, then we will take the general definition. So here, let's take this function fxy equal x power 2 y power 3 plus 2x plus 3y. So the partial derivative of the function f for x is the derivative of this function where y is considered as constant. So what is the derivative with respect to x of this function? This term, for example, the first term, y is constant. So it's 2x times y power 3. Then the derivative of the second term, this term, with respect to x, it's plus 2. Finally, the derivative of this term with respect to x, it's 0. Okay, now the partial derivative of f with respect to y. To calculate this, we will consider x as constant. So what is the derivative of x power 2 times y power 3? The derivative of y power 3, 3y power 2. So 3x power 2, y power 2. The derivative of this term is 0. Then, because this is constant for y, the derivative of 3y plus 3. Now, also we can calculate, we can take this term now here and calculate the derivative of this term with respect to x. So we will calculate the derivative of this term here with respect to x. We will use this notation or this notation, or it could be also the following notation. 2 d2 f and dx2. So up to for d, down to for x. Okay. So the answer is the derivative of this term with respect to x. So y is constant. So derivative of x times constant, it's 2y power 3. Derivative of 2, it's 0. Also here we can calculate the partial derivative of this term now, fy, with respect to x. So I will calculate the derivative with respect to x, so y as constant. So it will be derivative of x power 2, 2x times 3, 6x, y power 2, and derivative of 3 is 0. Also, we can use this notation like this, d2 f over d x dy. Okay. Here we have also a notation, an important notation. It's this notation. So we can write here, this is f xx. Okay. So this x, the first x here, then the second x comes here. So here I will write it like this, fy, then x, the partial derivative for x. So we can write it like this, f yx. Remark here, it's here dx dy, but here yx, the inverse. Huh? Okay. But it's not so important because we will see later that this will be the same as f xy by theorem. Okay, you will see this. This is equal because the function is continuous here, polynomial. So to verify, let's calculate this fxy. What is fxy? It's fx, then partial derivative for y. What is fx? Fx is calculated here. So let's repeat this term here. So it's 2x y power 3 plus 2, then partial derivative for y. So the derivative for y of y power 3 is 3y power 2. And 2x are constants for y. So 2x times 3, so 6x y power 2. So this is the final answer. And you can remark here that this answer the same as this answer. So this equality is correct. Okay. Now let's see the general definition of the partial derivative of a function fxy at a given point in the domain. If the limit given here on the right exists, this means it's a real number. If this limit exists, so this real number will be by definition the partial derivative of the function f with respect to x at ab. So the limit of f a plus h and b minus f ab over h. So if we note the function qx, let's note the function qx fxb and the function ry fay. So now this limit could be written as the limit of, so this term here, because here I have b constant here, fixed here, so it's similar to this one. It's q, limit of q, a plus h minus qa. This term here, qa plus h, qa plus h, and this term here is qa over h when h approaches 0. And this is by definition of a function in one variable. Qx is a function in one variable. So this is the derivative of q at a. And also here, so this term f a b plus h, so from here, it's r of b plus h. And this term is r b was yb. So I have the limit of r b plus h minus rb over h when h approaches 0. So this is by definition the derivative of the function r at the point b. So now we have the partial derivative of the function that could be defined also like the derivative of this function r given by one variable y, like this. And also the partial derivative with respect to x, it could be defined also as the derivative of the function q with respect to here, derivative with respect to x. Here in r, derivative with respect to y. Okay, let's take an exercise. Let fxy given by this formula, find the partial derivative of f with respect to x and the partial derivative of f with respect to y. So to calculate fx, I will consider y as constant. So here I have product. So derivative of the first, derivative of x power 2, it's 2x times the second, e power x, y power 2. Then here I have ln plus I plus the first times derivative of the second plus x power 2 times derivative of this term here y power 2 as constant. So it's y power 2 because derivative of x y power 2, it's y power 2 times e power x y power. Then let's take now this term here. The derivative of this term with respect to x minus derivative of 3x plus 5y, 3 over the term 3x plus 5y. Now the derivative of x over y. X over y could be written as x times 1 over y. 1 over y as constant. Alpha, it's like alpha. Alpha x, the derivative of alpha x, it's alpha. I have here plus 1 over y. So this is the partial derivative of f with respect to x. Let's calculate fy. X power 2 as constant. So I will check it side. Now derivative of e power x y power 2. Here the derivative with respect to y. So it will be a derivative of x y power 2. It's 2xy. 2xy times e power x y power 2. Now the derivative of ln 3x plus 5y. So I have minus here. 5 derivative of 5y. Derivative of 3x it's 0 over 3x plus 5. Then what is the derivative of 1 over y with respect to y? The derivative with respect to y, it's minus 1 over y power 2. So here, if I product by x, I can put x outside, so times x. So minus x over y power 2. The next exercise, let fx equal to x power 3 ln y. Find all the partial derivatives of second order of f. What is the meaning of the question? It means find fxx, fxy, fyx, and fyy. To find all of these derivatives, let's calculate at first fx and fy. So let's begin by calculating fx. What is fx? Derivative of x power 3, it's a 3x power 2. And ln y is constant. What is fy? Derivative of ln y, it's 1 over y times the constant x power 3, so x power 3 over y. Now let's continue. Let's calculate fxx. So the derivative of x with respect to x of 3x power 2, it's 6x, times the constant ln y, so 6x ln y. Now the derivative, let's take fyy. So the derivative of x power 3 over y with respect to y. So this is like x power 3 times 1 over y. What is the derivative of 1 over y with respect to y? It's minus 1 over y power 2. So minus x power 3 over y power 2. Now let's calculate fxy. So this means fx, then the partial derivative with respect to y. So what is fx? It's here, even here. So 3x power 2 times ln y with respect to y. The derivative give me derivative of ln y 1 over y. So 3x power 2 over y. Let's calculate fyx. So this is fy, then partial derivative with respect to x. So fy is given here. So it's x power 3 times 1 over y. The derivative with respect to x, y as constant, derivative of x power 3 is 3 x power 2 times 1 over y. So the answer is 3x of power 2 over y. We can remark that it's the same answer. So we can remark that fxy equal fyx. In fact, this is always correct if these two derivatives exist and continuous. This is a theorem. So let's see this theorem. Let z equal fxy be a function in two variables. And let's suppose that these two derivatives, partial derivatives, exist and continuous. Then, by a theorem, fxy, the partial derivative, fxy equal fyx. So these two partial derivatives are the same. Then after that, we can generalize this. So we can write that if we have fx, y, x, we can write it fx, x, y, or we can write here also f, y, x, x, etc. So we can commute all these partial derivatives. Even if we have a function u in 3 variables, x, y, z, f, the partial derivatives, fxy, fyx, fxz, fzx, fyz, fzy, if all of these partial derivatives exist and continuous, then we can write fzy, here no, here I will delete this, okay? So fzy equal fyz. So this is correct, and also fxz equal fzx, etc. Now, definition of differential of function in 2 variables. Let's remember before that the definition of the differential of a function y equals jx in 1 variable. So let's suppose that the derivative of this function exists, j derivative x exists. Then we note this derivative like this, y derivative or j derivative or dy over dx. So the differential of the function y or the function g could be written as dy or djx, or could be written also as y derivative dx or j derivative dx or dy over dx times dx. So the function y equal gx is called differentiable at a point A in the domain if the derivative at this point exists. In this case, we will write the differential here, the differential of the function g at the point A is given by this formula. So because this exists, this is a number, for example, 5, if it's 5, so the differential is 5 dx, where dx is the differential of x. Okay. So the definition of the differential of a function in 2 variables will be similar to the previous. So it will be defined like this. The differential of the function fxy is by definition, this equal with 2 points means by definition, equal by definition, the partial derivative of the function f with respect to x times dx plus, so this is a real number, the bound on x and y, plus the partial derivative of f with respect to y times dy. So for example, if I put here AB, so here I will put AB, and here I will put AB. Let's suppose that AB a point in the domain. So if the partial derivative of f with respect to x at AB exists, and also partial derivative of f with respect to y at AB exists, then the differential of f at AB exists and equal this term. So the function f is differentiable at AB if these 2 real numbers here, this real number and this real number, exist. The last exercise, let fxy equal the root of x power 2 minus y power 4. Find the differential of the function f. So the differential of the function f is equal. Let's repeat the definition. Fx dx plus fy dy. So let's write the partial derivative of this term with respect to x. What was the derivative of root jx derivative with respect to x? It's j derivative x over 2 root jx. So here it's the same, but I will take derivative now for x only, so y as constant. So derivative of x power 2, it's 2x over 2 root, because there is 2 here, 2 root x power 2 minus y power 4 dx plus, now the derivative with respect to y, it will be derivative of minus y power 4, it's minus 4 y power 3 over 2 root x2 minus y power 4 dy. For example, let's take the point x9, y3. Let's ask this question. Is the differential of f at the point 9, 3 exist? At first, is 9, 3 in the domain? Can we calculate f9, 3? Yes, we can. So it's root of 9 power 2 minus 3 power 4. It's root of 81 minus 81. So it's root of 0. It's 0. So it exists in the domain. So the 0.93 exists in the domain. But can we calculate the differential of f at 93? If I put here x9 and y3, so I will have here 0. So, and here x9. So 2 by 9, 18 over 0. So it doesn't exist. So it's not defined. Okay. So because f, partial derivative of f with respect to x at 9, 3, and also partial derivative of f with respect to y also here will be 0. If I put 9, 3 here, it will be here 0. Because this at 9, 3 doesn't exist. So the differential of f at 9, 3 also doesn't exist. But let's calculate what is differential of f, for example, at 1, 0. So if you put here x1, 2 times 1, it's 2, over x0 here, so 2 times root x1, y0, 1 minus 0, dx minus 4 times 0 over 2 times root 1 minus 0 dy. So the final answer is 1 dx. So this is the differential of the function f at the point 1,